Space, the ultimate frontier, a vast, uncharted expanse that has captivated the imagination of humankind for centuries. It is a realm of infinite possibilities where mysteries as old as time itself await discovery. From the glowing nebulae that birth new stars to the dark voids stretching across the cosmos, space holds secrets beyond our wildest dreams. For generations, we have gazed at the night sky, wondering what lies beyond our world. How did the universe come into existence? What forces shape the galaxies, stars, and planets? Are we alone in this infinite expanse, or do other civilizations exist, waiting to be found? Join us on an extraordinary journey through time and space. We will travel back to the very moment of creation, the Big Bang, witnessing the birth of everything we know. We will follow the evolution of the universe, from its fiery beginnings to the formation of galaxies and the emergence of life. As we venture deeper, we will explore the cosmic forces that govern existence, from the mysterious pull of black holes to the mind-bending nature of dark matter and dark energy. But the journey doesn't end there. As we look ahead, we will ponder the fate of the universe. Will it expand forever, grow cold, and fade into darkness? Or will the forces of nature lead to a cosmic rebirth? The answers may be hidden among the stars, waiting to be uncovered. Prepare yourself for an adventure beyond imagination, where science meets the unknown and curiosity fuels exploration. The universe is vast, and our journey is just beginning. As we venture into the depths of space, we confront one of the greatest mysteries of all. Does the universe have a boundary, or does it stretch infinitely beyond our reach? For centuries, humanity has pondered this question, searching for clues hidden in the vast cosmic ocean. Beyond the galaxies, beyond the stars, lies an enigma that defies our understanding, a realm we cannot yet see, yet one that stirs our imagination. Are we trapped within the limits of our observable universe, or is there something more waiting beyond the cosmic horizon? With every new discovery, we push the boundaries of knowledge, yet the further we look, the more questions arise. What exists beyond the edge of what we can see? Is there a multiverse, an endless sea of realities beyond our own? Or does the universe curve back on itself, an infinite loop with no true end? As we journey through the cosmos, we must accept that our vision is confined, limited by the very fabric of space-time. But with advancing technology and deeper understanding, we inch closer to unraveling the secrets of the unknown. The universe is a puzzle, and piece by piece, we strive to solve it. The answers may be just beyond our grasp, or perhaps they lie within us, waiting to be discovered. What lies beyond these cosmic boundaries remains one of the greatest mysteries of existence, a vast, unseen frontier cloaked in the unknown. It is as if over time, these regions have moved to much greater distances due to this relentless expansion, causing the boundary of the observable universe to extend far beyond what simple calculations might suggest. Yet, what lies beyond this limit remains one of the greatest unsolved mysteries in cosmology. The observable universe is merely a portion of the full cosmos, much like an island in an endless ocean. If the universe is finite, does it have an edge? Or does space curve in on itself in a way we cannot yet comprehend? If it is infinite, does it continue forever, filled with an uncountable number of galaxies, stars, and possibly even other life forms? Modern cosmology offers fascinating theories. Some suggest that space beyond our observable universe is similar to what we see, an endless continuation of galaxies. Others propose more radical ideas, such as the existence of a multiverse, where our universe is just one of many within a vast cosmic structure. Some models even hint at the possibility of entirely different physical laws beyond our reach, making the unseen regions of the cosmos even more mysterious. For now, we remain confined within the limits of what light allows us to see. But with advancements in technology, such as the James Webb Space Telescope and future space observatories, we may soon uncover new clues that push the boundaries of our understanding. The more we explore, the more questions arise, and the deeper our curiosity grows. One thing is certain: the universe is far grander and more complex than we can currently fathom. And as we continue our journey of discovery, we may one day glimpse beyond the observable and unlock the secrets of existence itself. The universe is vast, but our ability to perceive it is limited by the nature of light itself. When we look up at the night sky, we don't see an infinite sea of stars stretching in every direction. Instead, we see only those celestial bodies whose light has had enough time to reach us. This limitation is not just a matter of distance. It is dictated by the fundamental laws of physics that govern the cosmos. At a fundamental level, light sets a boundary on what we can observe. Every photon that reaches us has traveled across unimaginable distances, overcoming the vast voids of space. However, beyond a certain threshold, light simply hasn't had enough time to make the journey. This creates a kind of invisible sphere around us, a cosmic limit beyond which countless stars and galaxies remain hidden from our view. The two key horizons, the particle horizon and the event horizon, there are two crucial cosmological horizons that define what we can and cannot observe. 1. The particle horizon, the boundary of the observable universe. The particle horizon is the maximum distance from which light has been able to travel to us since the beginning of time. In other words, it defines the edge of our observable universe. A cosmic bubble with a radius of 46.5 billion light-years. Beyond this point, light simply hasn't had enough time to reach us, meaning we can never directly observe what lies beyond it. However, this does not mean that nothing exists beyond this limit. The universe likely continues far beyond what we can see, possibly even infinitely. But as far as our instruments are concerned, the particle horizon marks the farthest extent of the cosmic map we can explore. 2. The event horizon. The limit set by cosmic expansion. The event horizon is an even more perplexing boundary. Unlike the particle horizon, which is based on past light travel, the event horizon is determined by the future expansion of the universe. Due to the accelerating expansion caused by dark energy, certain galaxies are moving away from us faster than the speed of light. This means that even if they emit light today, that light will never reach us because space itself is stretching too rapidly. Essentially, the event horizon represents the limit of what we will ever be able to observe, even in the infinite future. Anything beyond this horizon is permanently lost to us, no matter how powerful our telescopes become. What lies beyond these horizons? Although we cannot directly observe what exists past these boundaries, physics and cosmology offer fascinating possibilities. An infinite universe. Many scientists believe that the universe extends infinitely beyond our observable region, filled with more galaxies, stars, and perhaps even planets like Earth. The multiverse. Some theories propose that beyond our cosmic horizon, other universes may exist, separate from ours, governed by different physical laws. A cosmic rebirth. Another possibility is that space beyond our visible region could hold clues about the universe's ultimate fate, whether it will expand forever, collapse, or cycle through endless rebirths. For now, we remain trapped within the visible sphere of our universe, bound by the limitations of light and cosmic expansion. But with each new into the unknown, unlocking deeper mysteries of existence. One day, our understanding of these unseen realms may change everything we know about the cosmos and our place within it. The limits of our cosmic vision, the particle horizon, event horizon, and Hubble horizon. Although the universe seems vast and boundless, our ability to observe it is limited by the speed of light and the nature of cosmic expansion. This creates different horizons, boundaries that define what we can see, what will ever be visible, and what is forever lost beyond our reach. 1. The particle horizon, the edge of the observable universe. The particle horizon marks the farthest distance from which light has reached us since the birth of the universe. This means that it defines the observable universe, a sphere roughly 46.5 billion light-years in radius. Beyond this limit, light simply hasn't had enough time to travel to us. However, this doesn't mean that the universe ends at this boundary. In fact, many scientists believe it continues infinitely beyond our view, filled with countless galaxies that remain hidden simply because their light hasn't reached us yet. 2. The event horizon, the limit of our future observations. While the particle horizon shows us the past, the event horizon is about the future. It marks the distance at which light emitted today will never reach us due to the rapid expansion of space. The universe isn't just expanding, it's accelerating due to dark energy. As a result, some galaxies are moving away faster than the speed of light. Even though light travels at an incredible speed of 300,000 kilometers per second, it cannot catch up to objects that are receding too quickly. This means that even if we waited forever, there are regions of the universe that we will never be able to see, no matter how powerful our telescopes become. These regions are effectively lost to us, hidden beyond an invisible event horizon. 3. The Hubble horizon, the limit set by cosmic expansion. Beyond the event horizon lies another boundary known as the Hubble horizon. This defines the distance at which galaxies and other celestial objects are receding from us at exactly the speed of light. Anything beyond this point is moving away too fast, making it impossible for their light to ever reach us, even if the universe existed for eternity. This creates the illusion of a limited universe. In reality, the cosmos may be infinite, but we are trapped within a shrinking bubble of visibility where more and more galaxies fade beyond our reach due to expansion. Why does light play such a crucial role? Everything we see in the universe is only visible because light from these distant objects has had enough time to reach us. However, light does not travel instantaneously. It moves at a finite speed. For example, the sun is about 94 million miles, 150 million kilometers from Earth. It takes light 8 minutes to reach us, meaning we always see the sun as it was 8 minutes ago, not as it is right now. The nearest star system, Alpha Centauri, is 4.3 light-years away, so we see it as it was 4.3 years ago. The Andromeda Galaxy, our closest major galactic neighbor, is 2.5 million light-years away, so the image we see today is actually what Andromeda looked like 2.5 million years ago. long before humans even existed. As we look deeper into space, we are not just looking across great distances, we are looking back in time, witnessing the universe as it once was. But beyond a certain point, light has not had enough time to travel to us, placing a fundamental limit on our observations. What lies beyond our horizons? If we could somehow break free from these cosmic limits, what would we see? Some theories suggest an infinite universe where galaxies extend endlessly beyond our sight, a multiverse where our universe is just one of many, each with different physical laws, unknown cosmic structures, possibly giant voids, hidden dimensions, or other exotic phenomena that challenge our understanding of physics. For now, we remain confined within the boundaries of light and cosmic expansion. But with every new discovery, we take one step closer to unlocking the deepest mysteries of existence. The universe may have its limits, but human curiosity knows no bounds. A light, the ultimate time machine of the cosmos. Every time we look into the night sky, we are not just witnessing the universe as it is, but rather as it was. Light, despite traveling at an astonishing speed of 300,000 kilometers per second, 186,000 miles per second, takes time to travel across the vast distances of space. This means that every celestial object we observe is a snapshot from the past, showing us an earlier version of the universe. For example, the Sun is 94 million miles, 150 million kilometers away, meaning its light takes 4.2 years to reach us. If Alpha Centauri exploded right now, we wouldn't see it happen until 4.2 years later. The HD-1 galaxy, one of the most distant known galaxies, is 13.4 billion light-years away. This means that when we observe it, we are looking at the universe as it was 13.4 billion years ago, not as it is today. Looking back in time, the cosmic time machine. This phenomenon turns telescopes into time machines, allowing astronomers to see into the past, studying the birth of stars, galaxies, and even the universe itself. When we look at distant galaxies, like HD-1, we are observing them as they existed when the universe was still young. This provides scientists with valuable insights into how the first galaxies formed, how early stars evolved, and even how the structure of the cosmos came to be. However, there are challenges. Light doesn't always travel in a straight path. It can be absorbed, bent, or blocked by cosmic obstacles such as interstellar dust clouds, which can obscure distant galaxies, gravitational lensing, where massive galaxies or black holes bend and distort light, black holes, which can completely swallow light, preventing any information from reaching us. The role of light in understanding the universe's evolution. Despite these challenges, light remains our most powerful tool in unraveling the mysteries of the cosmos. By analyzing the light from distant objects, astronomers can determine the composition of stars and galaxies, measure the age and expansion rate of the universe, uncover the origins of black holes and cosmic structures, predict the future evolution of the cosmos, what lies beyond our reach. Even with the most advanced telescopes, there are limits to how far we can see. Due to the universe's expansion, some regions are moving away faster than light itself. This means that certain galaxies will forever remain beyond our view, trapped behind the cosmic event horizon. But with every new discovery, we push the boundaries of human knowledge, coming closer to answering the ultimate questions. How did the universe begin? What lies beyond what we can see? Will we ever find a way to see beyond the limits of light? For now, we remain time travelers of the past, gazing into the ancient echoes of the cosmos, waiting for light from the deepest corners of the universe to reveal its secrets. Echoes of the Big Bang, the universe's first light. The story of the universe begins with a tremendous explosion, the Big Bang. This event, which took place 13.8 billion years ago, set the stage for everything we see today. But how do we know it actually happened? What evidence remains from this ancient cosmic birth? One of the most important clues comes from light itself. The cosmic microwave background radiation, CMB, often called the echo of the Big Bang, provides direct proof of the universe's earliest moments. The universe, before light, a cosmic fog. Immediately after the Big Bang, the universe was a chaotic sea of energy and particles. The temperature was so extreme that atoms couldn't form. Protons and electrons were constantly colliding and scattering photons, particles of light. This meant that light could not travel freely. Instead, it was absorbed and re-emitted in random directions, creating a dense, opaque fog. For the first 380,000 years, the universe remained in this blinding storm of energy, preventing light from escaping. The birth of transparency, the universe's first light. Then, something incredible happened. As the universe expanded, it cooled down. Around 380,000 years after the Big Bang, temperatures dropped enough for protons and electrons to combine into neutral hydrogen atoms. This was a game-changing moment. With fewer free electrons to scatter light, the universe became transparent for the first time. Light was finally able to travel freely across the cosmos, forming what we now detect as cosmic microwave background radiation. This radiation is the oldest light in the universe, carrying an imprint of the moment when the cosmos first became visible. It is essentially a baby picture of the universe, frozen in time. The accidental discovery of the universe's first light. For centuries, scientists debated whether the universe had a beginning or had existed forever. But in the 20th century, a surprising discovery changed everything. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Laboratories in New Jersey. They were testing a large radio telescope when they picked up a strange noise, a mysterious constant signal that seemed to be coming from everywhere in the sky. At first, they thought it was interference, maybe from the Milky Way, or even pigeon droppings on their equipment. But after thorough testing, they realized that this radiation was something completely new, what glow left over from the Big Bang itself. Their discovery confirmed the Big Bang theory and earned them the Nobel Prize in Physics in 1978. What does the cosmic microwave background tell us? Today, we can detect this ancient light in every direction, 13.8 billion light-years away. The CMB is not visible to the human eye, but special telescopes, like the COBE, WMAP, and Planck satellites, have captured detailed images of it. The CMB is a cold, faint glow that fills the universe, with a temperature just above absolute zero, minus 454 degrees Fahrenheit, or minus 270 degrees Celsius. But within this radiation, tiny fluctuations exist, small temperature differences that reveal the early structure of the universe. These tiny variations in temperature and density eventually led to the formation of galaxies, stars, and planets, shaping the universe as we know it. The universe's baby picture, how we use CMB to understand the past. By studying the CMB, scientists have been able to uncover critical details about the early universe, the age of the universe. The CMB confirms that the universe is 13.8 billion years old. The composition of the universe. It reveals that the universe is made of 5% normal matter, 27% dark matter, and 68% dark energy. The flatness of space. Measurements of the CMB show that the universe is almost perfectly flat, meaning space is not curved on a cosmic scale. Dark energy's role. The CMB helps scientists understand how dark energy is accelerating the expansion of the universe. The future of the first light. Though the CMB has been traveling through space for billions of years, it won't last forever. Over time, the expansion of the universe will stretch this radiation even further, making it colder and fainter. Billions of years from now, the CMB will become so weak that future civilizations may not be able to detect it at all. If this happens, future scientists may never know that the Big Bang happened. For now, the CMB remains a crucial window into the past, offering us a glimpse of the universe's earliest moments. As we continue exploring space, we uncover new cosmic secrets. But the first light of the universe will always be our greatest clue to understanding where we came from and where we are going. The cosmic microwave background, CMB, gives us a glimpse of the universe's earliest moments. However, we cannot see it with the naked eye. Its intensity is too low. This is due to the expansion of the universe, which stretches light waves, shifting them into the microwave spectrum and making them nearly invisible. Despite this, advanced instruments like the LHC, Large Hadron Collider, allow scientists to study this ancient radiation. By analyzing temperature fluctuations in the CMB, scientists have uncovered crucial insights into the evolution of the universe. These fluctuations, visible as hot, orange, and cold, blue spots, represent variations in early cosmic density. These patterns help scientists understand how galaxies and stars formed. The size of these spots also provides strong evidence that the universe follows a flat geometry rather than being curved. In 2003, astronomers found that dark matter and dark energy make up most of the universe. Dark matter, 26.8%, invisible mass shaping galaxies. Dark energy, 68.3%, causing the universe's accelerated expansion. Moreover, the CMB has helped determine the universe's expansion rate, currently at 42 miles per hour per megaparsec. While the CMB gives us a cosmic map of the past, our ability to see beyond is limited by space horizons. The question remains, can we ever look past these boundaries? The cosmic particle horizon marks the boundary of our visible universe, a limit beyond which light hasn't yet had time to reach us. Over time, as light continues its journey, we gradually uncover more cosmic objects. However, some things will always remain beyond our reach. But what if there was a way around this limitation? Enter the neutrino, a nearly massless particle that barely interacts with matter, allowing it to travel vast distances at nearly the speed of light. Produced in supernova explosions, nuclear reactions in stars, and cosmic collisions, neutrinos carry valuable information from across the cosmos, even from beyond our observable universe. Similarly, gravitational waves, ripples in space-time caused by massive celestial events, offer another key to understanding what lies beyond. In 2016, scientists at MIT detected gravitational waves from two merging black holes 1.3 billion light-years away, proving that these waves can reveal distant cosmic events long after they happen. Despite these breakthroughs, a fundamental challenge remains: the expansion of the universe. Since the Big Bang, space has been stretching, pushing galaxies apart. Dark energy fuel will never escape, currently set at 16 billion light years. This limit means that any message we send beyond this point will eventually be stretched into undetectable frequencies, making communication with extraterrestrial civilizations nearly impossible. So, while science continues to push the boundaries of our cosmic knowledge, some mysteries may forever remain hidden, just beyond our cosmic horizon. The future of the universe, a journey beyond the horizon. The expansion of the universe is shaping our cosmic fate in ways we are only beginning to understand. Right now, the event horizon is at 16 billion light years, but in the future, this distance will shrink, cutting us off from communication with even the galaxies we can currently reach. We will eventually be trapped within our own space bubble, isolated from the wider cosmos. Another critical boundary is the Hubble horizon, currently at 14.5 billion light-years, beyond which galaxies recede faster than the speed of light. Over time, the Hubble horizon will grow, allowing more distant light to reach us. However, one day, it will begin to shrink, locking us within a cosmic prison of local galaxies, with no new light or signals reaching us from the broader universe. In about 10 billion years, both the event horizon and the Hubble horizon will merge, forming a new 63 billion light-year limit. Beyond this, all light from distant galaxies will disappear forever. The universe seems to be closing in on itself, keeping its deepest mysteries hidden from us. The limits of human knowledge. Despite these cosmic boundaries, the rapid advancement of technology provides hope. Neutrinos and gravitational waves may allow us to glimpse beyond these barriers. In the far future, perhaps humans will expand beyond Earth, setting up observatories on other planets to extend our reach. While we cannot eliminate these limitations, we may one day learn to work around them. The human story is one of exploration. For millennia, we have gazed at the sky, charting stars, questioning our place in the cosmos, and pushing the limits of our understanding. But now, a new question arises. What happens at the end of time? We are on a journey to the very end of the universe itself, to a future where the fabric of space and time unravels. What will the final days of the cosmos look like? Will the universe end in darkness, destruction, or something entirely unforeseen? Let's step forward, not through space, but through time itself, to explore the ultimate fate of everything we know. A journey to the end of time, 385 AD. The return of an old friend. A brilliant streak of light cuts across the night sky. Comet Hale, Bob, has returned. Its glowing tail is a breathtaking reminder of the vastness of our universe and the fleeting nature of celestial events. 5000 AD, a planet transformed. The consequences of humanity's past choices are now undeniable. The polar ice caps have melted, leading to catastrophic sea level rise. Coastal cities, once thriving hubs of civilization, now rest beneath the ocean, silent relics of a world long gone. 6000 AD, an inevitable impact. A colossal asteroid looms on the horizon. Its path is set, its impact inevitable. The collision reshapes life on Earth, marking yet another chapter of devastation and transformation. 8000 AD, a cosmic explosion. Far beyond our solar system, a distant star collapses under its own weight, triggering a spectacular supernova. For a brief moment, its light outshines entire galaxies, a dazzling display of the ever-changing nature of the universe. The sun's reckoning, Earth's final days, 1 billion years from now. Our sun, the giver of life, burns 10% brighter than today. The heat becomes unbearable. Photosynthesis ceases, and the Earth's lush greenery begins to fade. 1.3 billion years. A dying planet. With rising temperatures, the oceans begin to evaporate, leaving behind a cracked, barren wasteland. The Earth, once a vibrant blue jewel, is now a lifeless brown sphere. 7.5 billion years. The end of Earth. The sun swells into a red giant, engulfing Mercury and Venus before finally consuming Earth. Our home, nurturer of life for billions of years, is reduced to cosmic dust, a universe slipping into darkness 10 billion years. The sun's afterlife. After its violent transformation, the sun collapses into a white dwarf, a fading ember of its former self. The once mighty star is now a dim, dying remnant floating in the void. 100 trillion years, a silent universe. One by one, the stars go out. The last of their light flickers and fades, leaving the universe in deep darkness. 1 quadrillion years, the cosmic winter. The temperature of the universe drops, marking the final descent into an eternal cosmic winter. The universe, once born in the fiery brilliance of the Big Bang, now drifts silently into the abyss. Though the universe may fade, the human desire to understand it remains eternal. This journey through time is not the final collapse, a new beginning. If the universe begins to contract, galaxies and stars would collide and merge, forming a blazing inferno of energy. Eventually, all matter and energy would be compressed into a single, infinitesimal point, a singularity. And in this extreme state, where the laws of physics break down, a new Big Bang could occur, giving birth to an entirely new universe. The ultimate revelation. This journey through billions, trillions, and quadrillions of years reminds us of one undeniable truth. Nothing lasts forever. Yet, in the cyclical nature of the cosmos, endings are often beginnings in disguise. Perhaps at the end of time, we will find the greatest revelation, that in an infinite universe, the end is merely the start of something new. The future of the universe, 100 million years from now. Narration. The universe is constantly evolving, shaped by the birth and death of stars, the collision of galaxies, and the unseen forces of dark energy. But what happens when we look 100 million years into the future? How will the cosmos change? And more importantly, what role will humanity play in shaping its destiny? The fate of stars. In the vastness of space, stars are born, burn bright, and eventually fade away. The life cycle of a sun-like star spans billions of years. As it nears its end, it expands into a red giant, swallowing nearby planets before collapsing into a white dwarf. But what if, in the distant future, humanity could control this process? Scientists of tomorrow may develop stellar engineering, the ability to extend or shorten a star's life. Imagine refueling a dying sun, preventing it from consuming its planets, or accelerating a star's collapse to harvest its immense energy. Such technologies could redefine the boundaries of life and survival in the universe. Galaxies in motion, but stars are only part of the story. Galaxies themselves are in a constant dance, pulled by gravity and shaped by cosmic forces. The Milky Way is on a collision course with Andromeda, set to merge in 5 billion years. But even before that, smaller galaxies will be absorbed into larger ones, reshaping the cosmic landscape. In 100 million years, our galaxy will have traveled nearly 1 million light-years, shifting into regions of space with different densities. This could trigger bursts of star formation or lead to their decline. The colors of galaxies will change as their most massive stars burn out, leaving behind cooler, dimmer remnants. The expanding universe. Yet the most dramatic transformation will not come from stars or galaxies, but from the universe itself. Space is expanding at an ever-increasing rate, driven by the mysterious force of dark energy. Over millions of years, galaxies beyond our local group will drift further away until they become nearly invisible. If the acceleration continues unchecked, the distant universe may disappear from view, leaving only a handful of galaxies within our reach. This isolation could mark the beginning of a cosmic dark age, where the energy needed to form new stars becomes scarce. The final frontier for humanity. This timeline presents both challenges and opportunities. If civilization survives and thrives, we may become an interstellar species, harnessing the power of entire stars, moving planets, and even altering the fate of galaxies. The concept of Dyson spheres, massive structures built around stars to collect energy, could become a reality. But if we fail to adapt, Earth itself may not survive the increasing heat of the sun. In a billion years, the planet could become uninhabitable unless we find a way to move it or relocate to distant worlds. The endless journey. One thing is certain: the universe is never still. From the birth of new stars to the slow fading of galaxies, the cosmos will continue its journey through time. And in 100 million years, humanity may look up at the night sky and see a universe completely different from the one we know today. The only question that remains: will we be there to witness it? Moreover, in billions of years, gas leakage may become too fast. In this case, absolutely nothing will be able to form. No stars, no galaxies, no life. The heat death will eventually come. The heat death is not related to the transformation of our universe into hell through the evolution of stars. Instead, it is based on the second law of thermodynamics, which states that in a closed system, entropy, or the state of disorder, increases over time. That means energy will dissipate in such a way that absolutely nothing will be able to form into something unified. You can think of it as heat energy leaving your cup of tea and dissipating into the room. Eventually, the temperature of the tea becomes the same as the room, so drinking it no longer warms you. Similarly, galaxies will be too far apart, and stars will start to fade because there will be no more necessary inflow of energy or matter for the evolution of stars, planets, or other space objects. The universe will become completely dark and empty. Dark energy may threaten not only heat death, but could also accelerate the expansion of the universe many times faster over the next 100 million years. If that happens, the universe could face absolute death. Stars will not just stop forming, as in the previous scenario. Nothing will exist, not even fundamental particles, since objects like stars remain unchanged and do not increase their mass through expansion. A future immeasurably fast expansion could overwhelm the stars, causing them to explode. Another scenario for the end of our existence is the Big Rip. It suggests that the acceleration of expansion probably cannot be influenced. In 200 billion years, it may become so fast that gravitational interactions will be broken. Planets will leave their orbits, and the electromagnetic force that maintains the integrity of stars will no longer be able to resist dark energy. Over time, even atoms will be torn apart. Some theories propose that after the Big Rip, everything in the universe could return to the first stages of the Big Bang. However, what remains in singularity may not resemble the plasma from the beginning of the Big Bang. It would be cold and dilute instead of hot and dense. This means that no matter how terrifying the hypothetical end of the universe may be, there is a chance that this end could be a new beginning. Another danger to the entire universe may lie within ourselves. We know that everything around us is made of atoms. Inside an atom's nucleus, there are two elementary particles, protons and neutrons. These particles are stable within the nucleus, meaning they cannot decay. But what if this is not necessarily true? The proton is one of the most common particles in the universe and can exist outside the nucleus. According to the standard model of physics, the proton cannot decay. However, newer theories, such as grand unification theory, which combines electromagnetism, weak interactions, and strong interactions, suggest that proton decay is possible. If protons begin to decay on a massive scale, in millions or billions of years, parts of the universe could cease to exist. Proton decay would destabilize the nucleus of atoms, producing decay products that could affect the entire structure of the universe. The destruction of matter could disrupt the entire galactic evolution. While this may not mean the immediate end of the universe, a large-scale collapse of protons could trigger an inevitable and catastrophic fate. Beyond proton decay, another hypothetical existential threat involves vacuum instability. You may have heard of the Higgs boson, a fundamental particle in the Higgs field, which permeates the universe and gives particles mass. The Higgs field could also determine the nature of vacuum states. While we think of vacuum as empty space, it contains quantum fields. If the universe exists in a metastable state, meaning it is in a false vacuum rather than a true vacuum, an event with enormous energy, such as widespread proton decay, could cause a shift into a true vacuum state. This would create a bubble of true vacuum that expands at the speed of light, annihilating all matter and fundamental particles in its path. Such an event would prevent any form of life from ever arising again. The universe, as we know it, will change over time and one day become unrecognizable. It will continue evolving, but like everything else, it will eventually fade away. We cannot predict exactly when this will happen, no matter how hard we try to look into the future. However, one certainty remains: humanity will continue making outstanding discoveries, and perhaps in 100 million years, we will finally unveil the full history of the universe and our place within it. Beyond the three spatial dimensions and the single temporal dimension we experience, theoretical physics suggests the possibility of additional dimensions. If such dimensions exist, they could potentially harbor alternative universes, each governed by its own unique set of physical laws. In this speculative framework, vast cosmic voids might represent areas where our familiar four-dimensional universe thins, giving way to these hidden dimensions. However, it is important to note that this idea remains highly theoretical, lacking empirical validation. While it inspires numerous scientific and science fiction discussions, it is not yet widely accepted by the scientific community. A more grounded explanation for these cosmic voids stems from quantum mechanics. Quantum fluctuations, spontaneous variations in energy and particle appearances, could have played a crucial role in shaping the large-scale structure of the universe. Shortly after the Big Bang, the universe was an extremely hot and dense quantum realm, where these fluctuations had significant influence. As the universe expanded, these minute quantum variations could have been amplified, leading to an uneven distribution of matter. Over billions of years, the regions with lower matter density may have evolved into the vast cosmic voids we observe today. Verifying this theory is challenging, requiring precise measurements of the universe's large-scale structure and a deeper understanding of quantum physics. However, if proven, it would establish a profound connection between the quantum and cosmic realms, linking the smallest and largest scales of existence. Another intriguing hypothesis delves into topology, the mathematical study of space and its properties. Topological anomalies, or defects in the fabric of spacetime, could have originated during the inflationary epoch, a brief period of rapid expansion following the Big Bang. While inflation smoothed out most irregularities, it might have exaggerated tiny fluctuations in spacetime, leading to defects where matter cannot easily accumulate. These defects could have evolved into the immense voids we now detect across the cosmos. Primary black holes provide yet another potential explanation for cosmic voids. Unlike stellar mass black holes formed from dying stars, primary black holes may have formed in the early universe due to extreme density fluctuations. Some researchers speculate that these black holes could be lurking within cosmic voids, exerting gravitational influence while remaining undetectable through conventional means. Their presence could actively clear surrounding matter, further deepening these vast regions of emptiness. Additionally, dark matter, a mysterious unseen substance that comprises approximately 85% of the universe's matter, plays a crucial role in cosmic structure formation. Dark matter forms vast filaments connecting galaxies, creating a cosmic web. If some of these filaments collapsed or disintegrated due to unknown forces, they might have left behind the vast cosmic voids we see today. This suggests that voids are not simply empty spaces, but rather regions shaped by the unseen interactions of dark matter and cosmic forces. The exploration of cosmic voids leads us to even deeper questions about the universe's origins. The Big Bang, which occurred approximately 13.8 billion years ago, remains the dominant explanation for the universe's birth. However, what preceded this event? Did time and space exist before the Big Bang? Or is the notion of before meaningless in a cosmos where time itself emerged from this singular event? The oscillating universe theory posits that the cosmos undergoes infinite cycles of expansion and contraction. According to this idea, each Big Bang is preceded by a Big Crunch, a catastrophic collapse of the previous universe. This endless cycle of creation and destruction suggests a universe without a definitive beginning or end. Another perspective is the multiverse theory, which envisions our universe as just one among countless others. Each universe within this vast multiverse may have different physical laws and histories, and interactions between these universes might even have triggered our own Big Bang. However, since other universes, if they exist, are beyond our observational reach, the multiverse remains a speculative concept without empirical verification. String theory, a framework that attempts to reconcile quantum mechanics with gravity, offers yet another explanation. It suggests that fundamental particles are actually tiny vibrating strings, and it predicts the existence of additional dimensions beyond the three we perceive. A variant of string theory, the ekpyrotic model, proposes that our universe was born from the collision of higher dimensional branes, membranes. If true, Our Big Bang might have been the result of such a cataclysmic event. A more radical idea stems from quantum mechanics itself, the vacuum fluctuation model. Quantum vacuum fluctuations continuously generate short-lived particle-antiparticle pairs. Some physicists speculate that our entire universe could have emerged from one such fluctuation, where a tiny quantum bubble rapidly expanded into the cosmos we inhabit today. Lastly, the Big Bounce theory offers an alternative to the traditional Big Bang model. Instead of originating from a singularity, the universe might have rebounded from a previous contracting state. Quantum effects could have prevented a complete collapse, instead triggering an expansion phase, the one we observe as the Big Bang. Each of these theories presents fascinating possibilities, but many remain unproven due to the immense challenges in testing them. However, they push the boundaries of our understanding, driving scientific inquiry into the deepest mysteries of the cosmos. As we continue to explore space and refine our theories, we move closer to unraveling the secrets of the universe and its origins. Beyond our known dimensions, a journey into the unknown. What if the universe we see is just a small part of a much larger reality? Scientists have long explored the idea that beyond the three dimensions of space and the single dimension of time, additional hidden dimensions could exist. These unseen realms might hold secrets beyond our comprehension. Some theories suggest that these extra dimensions could be home to entirely different universes, each with its own unique physical laws, forces, and even forms of life. If such dimensions exist, then the vast cosmic voids we observe in space might not just be empty, but could act as gateways where our known universe blends into these hidden realms. However, as fascinating as this concept is, it remains purely speculative. While it has inspired countless scientific discussions and science fiction stories, mainstream physics has yet to find concrete evidence supporting the existence of parallel universes or extra dimensions. Until we uncover proof, these ideas remain part of the great mysteries of the cosmos, challenging our understanding of reality itself. Quantum fluctuations, the invisible architects of the universe. As we journey through the vastness of space, we encounter an extraordinary idea, one that bridges the enormity of the universe with the subatomic world of quantum mechanics. This idea is rooted in quantum fluctuations, a bizarre and fundamental property of the quantum realm, where particles and energy constantly emerge and vanish in an unpredictable dance. These fluctuations create a restless, frothy sea of energy at the smallest scales, seemingly chaotic but profoundly influential. At first glance, this quantum activity may seem irrelevant to the grand structures of the cosmos. After all, what could tiny, fleeting particles possibly have to do with the immense, silent voids stretching billions of light years across the universe? The connection, however, lies in the very origins of our cosmos, the earliest moments following the Big Bang, the birth of the universe, and the role of quantum effects. During the first fractions of a second after the Big Bang, the universe was a fiery, ultra-dense point, smaller than an atom, but containing all the energy and matter that would eventually form stars, galaxies, and planets. In this unimaginably extreme state, quantum effects dominated the scene. Tiny fluctuations in energy, occurring at the quantum level, rippled through this infant universe, causing minuscule variations in density. As the universe rapidly expanded, a process known as cosmic inflation, these small fluctuations were stretched to cosmic scales. Over billions of years, These variations acted as the seeds from which galaxies, clusters, and cosmic voids formed. The empty, vast regions of space we observe today, known as cosmic voids, may be direct consequences of these early quantum disturbances. A universe shaped by the smallest forces. It is astonishing to think that the largest structures in the universe might owe their existence to the smallest possible physical phenomena. The connection between the quantum and the cosmic challenges our understanding of reality. How can the same principles governing the behavior of subatomic particles also shape the grand architecture of the universe? Modern physics continues to explore this mystery. Some theories suggest that even now, quantum fluctuations influence the fabric of space-time, potentially creating distortions and possibly even new universes in higher dimensions. Others propose that the mysterious dark energy, which accelerates the universe's expansion, might be linked to quantum processes at an even deeper level. While these ideas remain highly theoretical, they remind us that the universe is far more interconnected than we ever imagined. From the smallest fluctuations in empty space to the vast stretches of cosmic voids, everything is woven together in a tapestry of complexity beyond our current understanding. As we look up at the night sky, gazing into the silent depths of space, we are not merely witnessing emptiness, we are seeing the lingering effects of quantum whispers from the birth of the universe itself. Quantum fluctuations and the cosmic void, the universe's ancient imprints. As we delve deeper into the mysteries of the cosmos, we encounter a fascinating concept, one that links the tiniest quantum effects to the largest cosmic structures. This idea suggests that the vast empty voids scattered across the universe may not be random. Instead, they could be ancient imprints left behind by quantum fluctuations in the earliest moments of cosmic history. How quantum fluctuations shaped the universe. In the first fractions of a second after the Big Bang, the universe was a superheated, dense singularity, so small that quantum effects played a dominant role in shaping its future. Within this quantum realm, energy and particles constantly appeared and vanished in a chaotic dance. These quantum fluctuations, random variations in energy at an infinitesimal scale, did not remain insignificant as the universe underwent cosmic inflation, a period of rapid and exponential expansion. These fluctuations were stretched across vast cosmic distances. Some regions ended up with slightly more matter and energy, while others had slightly less. Over billions of years, these tiny variations amplified, leading to the large-scale structures we observe today. Galaxies, clusters, and immense cosmic voids. The great voids, shadows of the quantum past. The immense, nearly empty voids we observe in the cosmos today, some spanning hundreds of millions of light years, may be the result of these early quantum fluctuations. In regions where there was slightly less matter, gravity had less influence, preventing the formation of galaxies and clusters. Over time, these low-density regions expanded into the great cosmic voids, vast and silent gaps in the structure of the universe. In this sense, these voids act as time capsules, preserving the imprints of the universe's quantum beginnings. They are not just empty spaces. They are the shadows of the forces that sculpted reality itself, stretching back to the birth of time. An unfinished puzzle in modern physics. While this idea is supported by some aspects of modern physics, it remains a highly theoretical concept. Scientists continue to investigate whether quantum fluctuations alone are enough to explain the formation of cosmic voids, or if other unknown factors played a role. Additionally, questions about the nature of dark matter and dark energy, which influence the universe's expansion and structure, complicate our understanding. Could quantum processes also be linked to these mysterious forces? Could the voids themselves be gateways to undiscovered dimensions or alternative realities? For now, these remain open questions, inspiring both scientific research and imaginative speculation. What we do know, however, is that the smallest forces of the quantum world have left their mark on the larger scales of the cosmos, a reminder that in the vast interplay of reality, nothing is truly insignificant. As we continue to explore the mysteries of space, we are not just looking outward, we are looking back in time, searching for the echoes of creation hidden in the silent voids of the universe. Verifying such a hypothesis is a challenging task that requires precise measurements of the large-scale structure of the universe, along with a deeper understanding of quantum physics and cosmology. Nevertheless, the prospect of connecting the quantum realm with the cosmic, the smallest scales with the largest, is an enticing one. Another fascinating hypothesis delves into the complex and abstract world of topology, the mathematical study of space and its properties. In the context of the universe, topological anomalies or space defects refer to irregularities in the fabric of spacetime. Much like defects in a fabric, these anomalies may represent regions where the normal structure of spacetime is disturbed. But where do these anomalies originate? To answer this, we must travel back to the inflationary period of the universe, a fraction of a second after the Big Bang. During this ultra-fast expansion phase, the universe grew exponentially. Although inflation smoothed out the overall distribution of matter and energy, it may have also amplified tiny irregularities in the fabric of spacetime, leading to the formation of topological defects. These defects could have influenced the distribution of matter, preventing it from accumulating in certain areas, and ultimately contributing to the vast empty regions we know as cosmic voids. The study of cosmic voids would not be complete without exploring one of the universe's most mysterious objects, black holes. Specifically, we turn our attention to primordial black holes. Unlike the more familiar black holes that form from the collapse of massive stars, primordial black holes are theorized to have emerged shortly after the Big Bang. They may have been created by extreme density fluctuations in the early universe, offering profound implications for our understanding of cosmology. Irregularities in the fabric of spacetime could lead to the formation of topological defects. These defects may act as regions where matter struggles to accumulate, ultimately giving rise to the vast empty spaces we recognize as cosmic voids. The study of cosmic voids would be incomplete without examining one of the universe's most mysterious entities, black holes. Specifically, we turn our focus to primordial black holes. Unlike the black holes we commonly know, formed from the collapse of massive stars, primordial black holes are theorized to have emerged shortly after the Big Bang. They may have originated from extreme density fluctuations in the early universe, offering intriguing insights into the nature of cosmology.